All right, everyone, so today we are reviewing the three methods and things that we know about systems of equations so that we can take our quiz today. The first thing we want to talk about is what types of solutions there are for these systems of equations. And there's three types. We have one solution, no solutions, or the empty set, or infinitely many solutions. And each one comes from a different set of lines. The first solution, which is the one we're most familiar with, is if I were to have a line that comes through this way, and then maybe a line that comes down through here, I can see that these two lines intersect at the point 1, 3, and since they are both linear equations, that would be the only spot that they intersect at. So these lines we say are intersecting. When we have no solution or that empty set sign, that means that I have two equations that are perfectly parallel to each other. So they will never intersect because we have no solution. There is no point that these two lines are going to be the same thing. So we say the lines are parallel. And for the last one, when we have infinitely many solutions, that means that I have two lines that are actually the exact same line. So I would have my blue line and then my orange line. They're maybe just represented by having the same coefficients, just multiplied by 2. So we would say that the lines are the same. Now the next thing we would want to look at are the two methods we've talked about using for our systems. The first one obviously being graphing and being able to see, just like I've shown up here when we talked about our types of solutions, being able to see where each one lies. However, we don't always need to use a graph. Sometimes we can use substitution or elimination. And the easiest way to know when to use each one depends on the equations you were given. I know I'm going to use substitution for an example that only has one variable with just a coefficient of 1. So I have one y in this first equation, and that means that I can easily solve for y, get y all by itself. And to do that, I can add 7x to both sides. So this top equation would really say y equals 7x plus 6. Now what I'm going to do is I'm going to take this 7x plus 6 and plug it in for y in the second equation. So now I have 4x minus 3 times 7x plus 6 equals 16. Now, there is no more y in this equation, remember, because I've plugged in a new expression for what y was. So I don't write y in here anywhere. So now I want to multiply or distribute this negative 3 to both terms in the parenthesis set. So now I would have 4x minus 21x minus 18 equals 16. Well, I want to combine like terms, so I'm going to combine these x's together, and that would give me a negative 17x. And then I want to move my constant terms to all be on the same side. So this would be equal to 34. Well, I want to figure out what just one x is, not negative 17 x's. So I divide both sides by negative 17. And I would get x equals negative 2. Now that I've found what x is, I can take negative 2 and plug it in for the x up here in this equation that I already have y all by itself for. So I have y equals 7 times negative 2 plus 6. Multiplying 7 and negative 2 would give me negative 14 plus 6. So y equals negative 8. So you can either write this as x equals negative 2, y equals negative 8, or you can write your final answer as an ordered pair, -2, -8. If I were to use the method of elimination, I want to notice if any of my variables match up, if one of my variables has a multiple of the other equation. So if I have 3x and -2x, I know that I can't multiply -2 by a number to get 3, and I can't take 3 multiplied by a whole number to get -2. So that's not going to be quite as easy. Let's take a look then instead at if I look at my y's. I have 8y and 2y. Well, I can take 2y and multiply that by 4 to get 8, but what I also want to do is I want to make it so that they have the opposite sign. So I don't want them both to be positive, I want one of these to be negative. And I can change that by multiplying this second equation by a -4. So instead of multiplying it by just +4 to get both of the terms to say 8y, I can make this the opposite sign so that now instead of having to subtract the equation, I'm going to add the equations. So let's go ahead and multiply this by -4. So we would have 8x minus 8y equals 18 times -4, which would be -72. So now I'm going to ignore this equation and add together the top and this bottom equation. Well, if I'm adding my x's together, I would get 11x. I purposely made this so that I would get 0 y's, and that does check out. And -5 plus a -72 would give me -77. Well, I don't care about something that says 0, so really I just have 11x equals -77. So I can divide both sides by 11 to get x all by itself, and we find that x equals -7. Now I'm going to take this and plug it in for any of my x's in my equations up here. And I do actually like this second equation. The second equation said -2x plus 2y equals 18. I like that one the best because it has the smallest coefficients and it's going to be the easiest to multiply and divide with. So I take and plug in -7 for x. And now I'm going to solve for y. So I get 14 when I multiply those two together, plus 2y equals 18, minus 14 from both sides, 2y equals 4, divide both sides by 2, y equals 2. Again, you can write this as -7, 2, or you can leave your answer as x equals y equals. The final couple of generalized things I want to talk about is how you know when to use each method. For graphing, the only time it makes sense to use graphing is when both equations are set up in that y equals mx plus b. When both of my equations are already solved for y, it's easiest to use this equation to graph them. If we're using standard form, it's not going to be very easy to graph it. First, I have to put it in terms of slope-intercept form and then graph the equation and hopefully find a close enough to exact point where they're going to intersect. It's not the most accurate way either, but sometimes it can be easier to use. Substitution, I've already kind of talked about this, but for substitution, when you have one variable with a coefficient of 1. So in that last example I did for substitution, the y was the only variable that had a coefficient of 1. Everything else was a whole number. And that's easiest to do because the substitution method wants you to isolate or solve for one of the variables. And if one of them is already just a coefficient of 1, all we have to do is make it so that that variable is on its own for our equations. For elimination, the easiest way to know when to use elimination is when all coefficients are not 1. So in that last example, I had a coefficient with each of my variables. So that meant that it was going to be easiest to try and find some number that I could multiply each of them by to get what my variable that I would be eliminating is. One more thing I want to point out, when you're using any of these methods, or substitution and elimination specifically, if I were to come across something that says 0 equals 0, that goes back to my first few solution types. So if I get something that's not just a coordinate point, and I get in one of my equations 0 equals 0, they cancel each other out, that means that these equations are actually the same. So this would have infinitely many solutions. However, if I get something that's not a true statement, like 12 equals 1, that's not true. That tells me that these lines cannot intersect. Think of it as the slash mark going with the not equals in my empty set. So we would say there is no solution. They are parallel lines, they do not match up. As always, if you have any more questions, anything else that you need to talk about, please don't hesitate to ask. I will be available all the time during this quiz. With that, good luck, and I'll see you next time.